We're going to start with the first and the simplest method in supervised learning. This is linear regression. We're going to go over the definition, give you some of the known engineering application, which is data feeding. We're going to quickly explain how to solve it. We give you the closed form solution, and because this simplest model has it can be interpreted very well. So that's why in order to do that, we need to discuss about statistical property of the least square estimate. Once you can solve the model, of course, in order to interpret the model, you need to know what to be interpreted. And first of all is the accuracy of the model. And most of the typical questions would also be about is this variable included in the model significant or not? So this is the variable selection or the topic of deciding important predictors in the linear least square. Okay, to discuss about the linear regression, I'm gonna readily talk about multiple linear regression. This is about having a response variable y that can be explained by many predictors. Okay, so this is called a multiple linear regression. The relationship is a linear regression because the relationship between the predictor and the response is a linear function. Here, the beta k is called the regression coefficients. It gives a weight of how each xk has influence on the response. This is a scalar equation. Y is in R. X is a vector in Rn. Okay. So beta, the regression coefficient, is also a vector in Rn. In short, if we can write it in like the sum of beta k xk, you can write it as x transpose beta. Okay. There are several names for this relationship. The response, sometimes it can be called regressed variable, the explained variable, dependent variable. For x, it can be called predictor explanatory independent variable. So the whole point is that once you have when you have data set, you determine what would be the independent variable and assume the linear structure. Okay, so before jumping to some example, I would like to explain first how to represent it in a vector or in a matrix form. Okay, when we have this example, the example that we're going to give next is the response y, for example, is the number of product cell. Sorry, the amount of cell. Suppose you run a company and your company sells a product, right? So you're interested in exploring the estimate of the sell, how much you sell for your product, and then you also would like to explore a factor that caused the sale. In this data set that we borrow from the book is advertising data. You invest on many channels of advertising. There's going to be how much you spend on the TV ad, radio, or newspapers. Okay, because you believe that, okay, if you spend a lot on the TV, right, you run many ads on the TV, that would help you promote the product, and probably the sale quantity increases. And the same goes to other channels of this advertising. Okay, so TV is X1, radio is X2. I mean, X1 is how much money you spend on the TV ads, right? Is it the unit is in, in USD or baht, for example. Okay, Now, when you believe you're the one who assume that the sale and the advertising budget has a linear relationship, but now what you would like to know is in the linear regression, you would like to determine these regression coefficient. Because once you have that number, beta 1, beta 2, beta 3, okay, it gives you how much influence of each predictor has on the response variable. Okay, so in order to do so, usually you collect data set. Okay, so suppose you have m samples, m measurements, which means for one instance, you know that you can sell for $1,000 on your product when you spend maybe $10 on the TV ad, and you spend 25 on the radio, and spend maybe $5 on the newspaper. Okay. In another instant, another realization of data, probably you have the sale of 2100 USD with other values of advertising budget. 5, maybe 600 on the radio, maybe 200 on the newspaper. All right, and you get a bunch of them, and that's what we mean by having this data set. Okay, now from that equation, so I'm going to repeat that equation, y equals x1 beta 1 dot xn beta n. Now I'm going to use the notation y1. This is for one sample, one data point of the response. Okay, so for the first row is again the first sample of all the predictors. So the row index represent the sample index, okay, and the column index represent the ith component of the predictor. So once we collect, sorry, this is supposed to be n. Once we collect the big N samples, all right, I call this guy a vector y, and this is a big vector x, and this is the regression coefficient. We end up with having the vector equation y equal x beta. The matrix X here has the size of big N by small n. Okay, this is called regressor matrix that obtained from the measurement of your predictor variables. The question in the multiple linear equation is there a way to explain this linear relationship? How can you obtain or estimate? How can you get the parameter beta out of this data set? Of course, if you look at this as as an equation, and typically when most of the time the data points or the big N will be large. Most of the time, you tend to have more data points than the number of variables. Or even that is not the case in your application, we will learn that usually we can learn that in principle that the more data you get, the more accurate or the more reliable of your regression coefficient will be. So all I'm saying that is that when we look at the vector equation here, the vector x, the matrix x tends to be a tall matrix. It doesn't have to be square, right? So which means when x is a tall matrix, you have the overdetermined linear equation. And of course, an exact solution to this equation usually doesn't usually exist because it depends on y. And I would like to also mention that most of the time, these y, if you think about real application, these y and these y come from sensor, come from the measurement. It also contains, corruption by noise. So it's nearly impossible to solve this equation exactly. The point of linear regression is, now you look at the problem again and then say that, I'm not gonna solve this equation exactly, but I'm gonna look at linear least square formulations. So the problem statement of a linear least square come from this setting that you assume the linear relationship between y and x, all right? But then because of when you observe these response variable y, there's a corrupted noise. And most of the time, the number of data points is more than the number of variables. So big N is bigger than the small n. N is the number of regression coefficient. All right. So big N is the number of sample. Okay. The definition of the linear least square is not to solve these over-determined linear equation, but they're going to measure the distance between the output. This is the output of linear model, and this is the actual y, the measurement. We look at this as the residual error. E equals y minus x beta. Okay, and let me let me represent this again in terms of vector notation. Okay, when you have from this representation, this is matrix X. You can also represent X as many rows. You can also say that this X can be partitioned into big N rows. Okay. The first row corresponds to this vector x1 transpose. The second row is x2 transpose, which means the equation y equal x beta can also be represented as each entry, all right, equals to the first row of the regressor matrix transpose with beta, the second row transpose with beta, and so on. Okay, and now when we look at the residual, which is y minus x beta, that is y1 minus x1 transpose beta, and so on. All right. The definition of linear least square formulation is that, okay, when you have the residual vector r that I represented previously, this is r1, r2, rn, okay, you aim to minimize this error. You want this residual to be as small as possible, but then the way you interpret this, the size or the magnitude of this residual vector is to use the true norm. And of course, the true norm is defined as the sum square of each of all the components. Okay. So the linear least square formulation is that, all right? So by what choice? So you have a choice on the regression coefficient beta. Beta is going to be the one that minimizes the true norm. Okay. Another notation is that it's going to be equivalent whether you square the residual norm or not. All right, with or without the square term, the the solution beta would be the same. Okay, so if I write it again, so it's going to be the sum of yi minus xi transpose beta square I from 1 to big N. Okay, this is a problem statement of linear least square. Now let's take a look at some graphical illustration. Okay, as we mentioned previously, we have the cells, all right, as the response. We have the number, the amount you spend on the TV ad, radio ad, all right, and the newspapers. Now let's take a look at probably just a first simplest example. where you are interested in only a relationship between a cell and one predictor. This is a TV, this is a cell. So the meaning of the linear least square is that, of course, you think that cell is proportional to TV, all right? By proportion, it means that you assume the linear relationship. The blue dots here are data points. These data points give you a pair of TV and cell, all right? The linear regression problem would be finding a straight line, a linear function that best fit the data points. And what we mean by the best fit is, as mentioned previously, that you're gonna measure what? The distance, right? The distance between the response and the output of the model. Okay, you measure it, use the two norm distance. So in this graph, the red line is our model, the linear model. The blue one is the other points. So what we do in the linear least square is we measure the the distance between data points and the model would be the height, right? The distance between all those points to the straight line. And what? And the objective of linear least square would be you minimize beta. Sorry, you minimize the sum of what? Of all yi minus xi transpose. In this example, your x is only one variable because it's only TV, all right? So it's xi times beta square. So it's a sum of all the ri square, I from 1 to big N. So you take the sum square of these error, all right, these vertical distance. The straight line, and by finding beta, it means that you're finding the best slope of this straight line. Okay. It depends on you if you want to include the intercept term or not. The intercept term is this, right? So if you include the intercept term, it means that you want to find the straight line with the optimal slope with the optimal intercept that makes sum square of this error minimized. Now let's take a look at a more general setting. Okay, when you regressed on two variables, suppose your y is can be explained by x1 and x2. Okay. Now, now of course, the relationship between model output and the predictor is linear, but now your variable has two components. Okay, and that relationship can be graphically explained as hyperplane. Hyperplane. All right. So the yellow one, the yellow dots here are the actual response, like y1, y2, and y4, things like that. Okay. Finding the least square solution would be the problem of finding beta 0, beta 1, and beta 2, which is actually characterize the, like, how you tilt or how you adjust the parameter of hyperplane. You know that beta 1 and beta 2 is actually the normal vector of the hyperplane. How this hyperplane can be selected? That's the choice of beta. Okay, according to the meaning, yet again, the meaning of the linear least square is to minimize the two norm or the two norm square, right? So graphically, what does it mean? Napat. Napat.
Up.
So the distance here that we see that in the mathematical formula, right? Or that I just explained as this, right? Is actually the sum, right? Sum square of error between a data point, right? To the point on the hyperplane. The point on the hyperplane is actually the output of your model. All right. So for one I is the distance of one point, one data point to the hyperplane. In this graph, how can you illustrate the distance from a data point to a hyperplane? Napat.
ก็คือลากจาก point ลงมาตรงๆลง hyperplane ครับ
Okay. So what you do is the distance is, so it's going to be, I mean, of course, when you, now Napat, suppose the hyperplane is this and your point is here, right? Your point is here. So it's going to be like you have like when you measure a descent from a point to a hyperplane, the way you draw has to be orthogonal, right? Orthogonal to the plane. So you measure that distance. You measure that distance for all the points, and you make this is the distance, right? And you make the sum square. Okay. So the best hyperplane actually characterize the least square solution because, as I said, beta 1 and beta 2 explain the normal vector of the hyperplane. Okay. The first and of course the most basic illustration of the linear least square is the problem of data fitting. Okay, in this case, just like the graph that we had, we have data point, right, and we would like to come up with a way to fit this data point by some explicit mathematical function. In that setting, the setting is we have the data point as point y and the coordinate ti. Okay, and you would like to approximate y with a function g. Then the function g conceptually is the function g can be decomposed as a sum of basis functions. Okay, the function g can be described as a linear combination of gk. For example, what you've seen before in engineering, gk, these are polynomial functions. So each term is the constant term, linear term. The next term is t squared up to the term t to the n. Or the basis function can be sinusoidal function. All right, sinusoidal function at different with different frequencies. Okay, so this is the concept of Fourier series as well. So in the data fitting, given this data set, how can you formulate into a linear regression form? All right. But by this, the choice of the basis function must be given. You have to decide, I'm going to fit the data by polynomial functions, for example. And then, of course, you iterate the equation. At point 1, y1 is going to be satisfied at t1, right? But at t1, gt1 is beta 1, g1 at t1, b plus beta n, gn at t1, right? And that's how you get the first equation. And you can repeat this equation that has to be satisfied for all data points. And now you get, again, just like before, the matrix equation. Sorry, it has to be n, big N, sorry. Okay. So please remind that these coefficients x is known and given. Because when, for example, with the choice of polynomial function, this x would be 1, t1 squared, t1 to the n. What about the last row? Can someone give me the last row? Thiravat?
ครับฮัลโหล1 tn
t subscript n, yes,
and tn square
tn square
and tn to the n
to the small n. All right.
yes.
This one again, the matrix x is known, is the value that you calculated from the data point. All right. So problem solve the data fitting problem is then to find the best linear combination coefficients that makes the function gt best fit with the data points. This is already done, as I said, the very established, or you can find numerical library in many language, Python or MATLAB. All right, very you don't even need to like calculate the matrix X yourself. This become like a very nice GUI. You just feed the data point. But the principle behind is this. All right, one you have X, one you have Y. You just solve the linear least square problem, which means you solve this mathematical problem. Okay, now I give you some example, the results. I have data points, all right? I have data point ti, yi, but my data points actually generated from these ground truth function, which is nonlinear. Okay, so my actual data point is the blue. These are the blue one. All right. In practice, the behavior or the ground truth characteristic of the data points is unknown. All right. So in this example, I illustrate the problem that what you know is these data point, and I would like to fit it with some known functions that I choose it to be a polynomial function, and I fit it with the 6th degree. Okay. Of course, from these data point, you can see that, of course, it should not be first fit by a straight line or the first order polynomial, because that obviously give you a very large bias, right? It doesn't explain just using the linear function doesn't explain the data points at all. Okay, I'd like to characterize the how it works. So basically, your y, which is the data point, right, is gonna be a linear combination beta 1, x1, beta 2, x2, beta n, xn, and your x1 is actually what the the linear function in the linear term in the linear function in the polynomial function. X2 is the square term and xn is the t to the n. If you look at the graph on the right hand side, I explain how each term contribute, you know, as like if you break down the rate curve into the decomposition of all these components of polynomial. Okay, you see a constant, the intercept term. You see kind of parabola from the quadratic term and so on, right? And all of these things, when you add them up, it gives the characteristic of the 6th order polynomial. The interpretation of this is the following as well. You have a nonlinear relationship, all right, the nonlinear relationship between y and t, but then as I said, this is typically unknown, all right, and you see that you can use polynomial function that has linear characteristic, nonlinear with the quadratic term until t to the n. All these terms are nonlinear, and if you can increase the polynomial order, you can explain some detail of these data points. For example, if you look at this tail, okay, when you see a ripple here in your output, that can be possible when you use a more complex or a higher degree of polynomial function. Okay, now we give you some application, but this is the important result, that how can we solve the least square problem. Before going to say that, I just give you the closed form solution, because the least square can be solved analytically. Okay. You want to minimize y minus x beta 2 norm square. Okay. And then if you look, take a look at this equation. Look at this function. I'm going to see how I should explain it. This is can be written at y minus x transpose, y minus x beta, everything transpose, y minus x beta, because the norm square of any vector is the inner product of y with itself. Okay. Okay. So now, if you can, if you if you expand this quadratic term, you will recognize that this is actually the quadratic function in beta. Okay, with minus 2y transpose x beta. Okay, and plus y transpose y. Okay, now we take a look at this as a function of beta, because we're going to minimize it with respect to beta. And when you take the gradient, okay, the gradient of this gradient is the derivative, all right? The gradient of this function would be 2x transpose x beta minus x transpose y equal to 0 with the factor 2. So you have these two. Okay. Why do I set it to 0? Because that's from calculus, right? You have minimization of some function, and that unconstrained problem, the optimality condition, or the condition where the optimal solution needs to satisfy is that the 0, you take the gradient and set it to 0. Okay. If you need to spend more time on verifying this, please go back, review the concept of gradient, all right, the derivative of the function of several variables. But then the point is, the more important point is that the 0 gradient condition, okay, if you just move around the equation, move this guy to the right hand side, this is called a normal equation. It becomes a linear function in beta with the coefficient matrix x transpose x, and this is something like a constant vector on the right hand side. Okay, now let's take a look at the dimension. The vector x, the matrix x is a matrix, the regressor matrix of size big N by small n. So x transpose x is going to be small n by small n. Okay, beta is, of course, regression coefficient is small n by 1. This guy is certainly n by 1, small n by 1. Recall that the least square problem originally is an optimization problem, but the optimality condition turns out to be just simply solving a linear system. And it is a linear system with the coefficient x transpose x, which is a square matrix. Square matrix. So you have a square system. Moreover, more important point, we know that in linear algebra, the matrix X transpose X is always positive semi-definite because it looks like a quadratic form in X. Okay, if if the matrix X transpose X is invertible, of course, beta has this closed form solution. All right, to solve the linear equation under the condition that X transpose X is invertible. The matrix the matrix here has a nice property that it is a left inverse of X, because if you multiply this guy 2x on the left hand side, the result is Sukit.
Is equal to
Identity matrix. Okay, so this is a definition of the left inverse. All right, a left inverse of X is any matrix that multiply to X on the left hand side and gives identity matrix. Which means another interpretation is we cannot solve this, we cannot solve y equal x beta exactly because x is tall, all right? But when we solve the problem in the linear least square sense, okay, the beta with this choice is actually, it doesn't look like, I mean, if this were a square system, you would say, oh, my beta is x inverse y, right? It was a square system. But I mean, in practice, it is not a square system, but because it's overdetermined. Solving the linear least square problem give a sense of, oh, your beta is some kind of pseudo inverse. And that pseudo inverse is a left inverse of x. Okay. Now we have a very important condition, as we mentioned, that this matrix has to be invertible. All right, otherwise the least square solution is not unique. All right. That assumption can be obtained when rank X is small n. The matrix X is tall with the big N rows and with the small n columns. So rank of X, you know that rank of X is the number of independent columns in X. So when we say rank X equals small n, which means we assume that that X is full column rank. Okay. And because the rank and the nullity, this is called the null space of a matrix X, all right? By the rank nullity theorem, please review. By rank nullity theorem, if rank X is small n, is full column rank, the null space of X is zero, is a zero space. So there cannot be a non-zero vector that lies in the null space of X, and that makes X transpose X positive definite. Not only that it's positive semi-definite, but it is positive definite. Okay, there's gonna be a simple homework problem probably to verify this important fact. All right. Okay. What's the interpretation of the rank X equal n? Full column rank. Remember that each column of X actually contains samples of of one predictors. So this is the predictor 1, this is predictor 2, this is predictor 3. Okay. So let me make an example that violate this rank condition. Okay. For example, if my first column is X1, okay, I collect X1 TV ad, just like the example. What if I include the second predictor in the model as some constant times the amount you spend on TV ad. So this is 2x1. And let's say this is x3, this is radio. With this example of including these predictors in the model, obviously rank X is not 3, but it is
2
because
because the first and second column is not independent.
yes, because the first 2 columns are dependent, right? Because the second column is just a multiple of the first one. So this is an example of how the rank condition violates the assumption that require for the least square solution to be unique, all right? So the interpretation is if you have 2 predictors, all right, that are dependent, then you shouldn't include them in the model. Why would you include 2 times TV in the model? That is redundant, right? Just exclude it. In the real data set, there's a chance that this condition is violated when the 2 columns, like when any 2 column is very highly correlated. Okay, highly correlated. Because it means highly correlated means one column is almost as if a multiple of another column. That's why when we talk about the variable selection, variable you include in the model, not only that it has to correlate with the response, but among the predictors you should, I mean, it would be best if all those predictors are dependent, okay, are independent, sorry. Okay, geometric interpretation of the least square solution. Okay. Emphasize here, beta is x transpose x inverse x transpose y, all right? You have a vector y here, all right? You want to minimize y minus x beta with the 2 norm square. If I draw a line py, which is x beta hat, all right? Suppose this py is the best prediction of y in the least square sense. Okay, once you have solved beta, of course the prediction would be x beta hat, right? And if I plug it back, the expression of beta, so it's going to be x times x transpose x inverse x transpose y. Okay, so this is my y hat. My y hat can be expressed as some matrix, all right? So I call it P, that P times with y. The interpretation is the following. Because you aim to pick beta that minimize these 2 norms, right? So it means that error, this is the error should be this vector, right? This vector E is minimized. All right, this E is minimized at this point. And what about the property of the y hat? because y hat is x times beta. So it is actually an x times beta. Again, I'm going to write it in another representation. If I partition my matrix X that has n columns, I partition it into column x1, column x2, dot column xn. All right. Of course, I would be able to write it as a linear combination of each xi, each column of the regressor matrix X. Okay. With this, of course, from linear algebraic point of view, it would mean that when you have y hat equal x beta hat, right? That must be because beta hat times is multiplied with x on the right hand side. Any vector y hat must be in the range of x. Right? That's the definition of the range of x. So which means y hat here, the graphical interpretation, it would lie on the range of x. Because in here in this graphical in this graph, so it's a linear combination of the second column and the first column of the matrix X. It can be shown, and it is very important property, that of course with the solution that py or y hat, it exactly like this vector that gives you the minimum e, the minimum length of e measured by the 2 norm. All right, this y hat is perpendicular to the error, or what we call in another term that y hat is orthogonal projection of y. When you project something, you project it on some space, and this is, in this context, is orthogonal projection on the range of x. Okay. Which means we can show that y minus y hat is orthogonal to y minus y hat is the error, right? Is orthogonal to any vector on the range of x. Or if you translate in mathematical terms, so inner product between y minus y hat, inner product with x and with any beta is always with x times any beta is always 0. Sorry, not with any beta. You can also write it with this term. I believe that you can write it that y minus y hat, right, inner product with any column of x must be 0 for all for all columns. Okay. Once we have solved linear regression, so then what we see here is the closed form and analytical expression of the linear least square. All right. For actual numerical computation, we didn't include that in this lecture, but I remind you that in library or software package, it doesn't solve the least square solution using this exactly expression. All right, it uses QR factorization and all of that. So once we have solved the model, okay, we can ask a lot of questions. Okay, this is some example from solving simple linear regression based on advertising data. If you regress the cell on each of the advertising cost, so first of all, if you regress cell on TV, okay, so this is just one simple linear regression. you got this straight line. So compared to, so if you look at this graph, what would you see? It seems that it's convincing that the cell and the TV relationship has some kind of a linear relationship, right? And when you look at what about the newspaper? Maybe the data point is more more widely spread, right? Like if you look at the newspaper, okay. So when we interpret the when we interpret the linear regression model coefficients, so in the multiple linear regression, if you regress y on all of the predictors, so beta j, beta 2, okay, beta 2 is going to be the average effect on y when you have 1 unit change in x2, when considering that all the other predictors fixed. Okay, so that's the interpretation. So for example, beta 2 is what? Is radio. Okay, okay. So if the beta 2 is 5, right? Is 5, the value is 5. It means that if x2 is changed by 1 unit, all right, the amount of cell would be changed by 5 when the other predictors are hold constant. Okay. So we're gonna go to the numerical examples later, but I would like to spend maybe half an hour here to analyze some property of the least square estimate. In the linear least square setting, one point is that when you solve this problem, okay, all of your data are random. But like think about how you collect a y and x, right? So, and when you have seen the expression of beta that is a function, is actually a function of x and y, right? So it means that when your data are random, both x and y are random, your beta hat, the least square solution, is also random. So that's why we need to analyze this property using some statistical tools, because it means that the point estimate, the value you estimate from that one data set, it's just one estimate. Okay. When you have another data set, your solution, your beta had changed. Okay. So in this setting, I would like to express the analysis in a simplest form, which means this is a form where I assume that the data are generated from this model. This is called linear additive noise. Okay, and the noise U, or the error term, is assumed to be white, which means, so this is the vector equation. My UI, okay. The data, the error term is white, UI, the correlation between UI and UJ is 0. But this is what we mean by white noise when I is not the same as J. It has 0 mean, okay, and and it has the covariance sigma. Okay. So sigma will have a structure that, Sukit, what would be the structure of sigma?
Yeah, it's a diagonal matrix.
Yes, it's a diagonal matrix because we assume that UI and UJ are uncorrelated, right, from the definition of white noise. So, but the thing is, what do we say in the diagonal term? What does it mean?
It's supposed to be 1, right?
No, the meaning is this is the variance of UI, okay? That now I leave it to be any general number, non-negative one, positive, all right? Okay, now I also assuming from this setting that the regression matrix X is deterministic. Just assume that it's constant, it's non-random, so that the analysis here is simple to follow. Okay, first of all, we can say that the least square estimate based on this setting, it has a nice property that it is unbiased. So the definition of unbiased estimator is defined that if your beta hat, right, the estimate, I said that it's random, right? Now it's random because of y, right? Your X is assumed to be deterministic, right? But your U is noise, is random, so your Y is random. When your Y is random, your beta hat is random. But the first property, we see that expectation of beta hat. I mean, beta hat is random, which means one data set. So this is the axis of data set. Suppose we have a bunch of them, all right? So the first data set, my beta hat is here. The second data set, my beta hat is here. All right, and so on. When I look at the mean, the expectation of beta hat, so I look at what? I look at the, of course, I tend to see that in average, right? In average, sorry, I should write a straight line. Okay, maybe an average, the green line. I would like to examine if the ensemble average of my estimate beta hat would be exactly the same as the true parameter. The true parameter that hidden in the true model. But this value is never known. Is typically unknown. Okay. The result is positive. That it does say that with this setting, your least square estimate is unbiased, because we can show that expectation of beta hat is, okay, now you're going to use the expression of beta hat, which is X transpose X inverse X transpose Y. And then you try to characterize this expectation. Now, next, Next, we're gonna kind of like break down this expectation. We know that this X is deterministic, right? Which means what we can do is we can take it out the expectation, like, because the only thing that random here is Y. What is the expectation of Y? Panat, take a look. Now we're gonna use the information from data generating process. If you look at this equation, what is the expectation of Y, Panat?
Expectation of X beta plus U. And then U is 0. Expectation of U is 0. So it will be expectation of X beta.
Okay, because we assume, right, by the setting that the noise is 0 mean, so this term goes to 0. What about the first term, Panat? Panat.
ครับ
X is assumed to be deterministic, while beta is a true parameter that is unknown. But it's a true parameter, so it's not random. So expectation of X times beta should be
X beta.
Yes, right? It's not random. So this guy is X beta. Can someone multiply this for me? True.
Yes, actually.
Yes, multiply it for me. I put it back, multiply this out. X transpose X, everything inverse, multiply with X transpose X times beta is,
Ajahn.
yes, okay, the first two terms is identity. I times beta gives me, I times beta is, I times beta is identity. Identity matrix times anything is
Beta.
beta, all right? Okay. All right, which means with this setting, it means that the ground truth model X and Y also has a linear relationship but corrupted by noise. Luckily, that noise is zero mean. Luckily, that noise is zero mean. When X is deterministic, it turns out that my least square estimate is unbiased because I can show that expectation of beta hat equals to beta. All right. It doesn't say that for one data set, my point estimate would be the true parameter. We don't say that, all right? But we say that if you have bunch of them, we have bunch of data set, bunch of realization, and you take the average, ensemble average of all the least square estimator, overall in average, your estimator, I mean, it has the average of the true parameter. So this is a positive result, like favorable result. The more important, oh, I shouldn't have deleted. The next question is to look at the beta hat from the F expectation. It's like looking at the first moment of this estimator. Okay, like beta hat is random. Of course, it's gonna have some distribution if we know distribution of y and everything, but here we just examine only a few moments of beta hat. The next question is we would like to examine the second moment. We would like to characterize the covariance of beta hat. Because of this reason. Okay, next, if I say, suppose you are just like the previous example. So this is again the axis of data set, right? Suppose the average, right? So what I mark is the point of beta hat. And of course, in average, my beta hat will have the mean according to the green line, right? Suppose the green line is also close to the two parameter. The second scenario is this. The average of your estimate is also represented by the green line. Suppose it's also close to the two parameter as well. What would be the difference between these two scenarios? If you look at how the beta hat spread over different data sets. Sukit.
The light one have more variance, like.
Yes. All right. So because the green line represents its mean, right? So it looks like the right one, the right scenario, your least square estimate, like widely spread. It has more fluctuations, which means in these two scenarios, I assume that they both have like pretty close mean to the true parameter, which means if you look at the bias alone as just one aspect, your least square has a favorable result, is unbiased. But the second moment can give you another dimension, another aspect that let's see how much fluctuation of your estimator is, because it's going to give us a sense of how we can rely on this estimate. So that's why we characterize the covariance of beta hat. That's the whole point. All right. Now, my beta hat again. My beta hat has has the closed form expression as this. Okay. Now, Sukit, don't please explain that beta hat. What kind of the linear the relationship between beta hat and y is linear or not?
It's linear.
Is linear, right? Is linear. So when we assume that x is deterministic, you can take a look at this guy in as a matrix gain, as a constant matrix. So Sukrit, what is the covariance of beta hat in terms of the covariance of y? This is F5 transformation.
Is the red box and covariance of y, and then the red box inverse.
Inverse. Is it the inverse, Sukit?
Is a transpose.
Is the transpose. Okay. Now, so we're gonna characterize this, all right? I think. Okay. What is the covariance of y? Now we're gonna take a look at we're gonna use the information of data generating process. Okay, what the covariance of y is going to be, what the expectation of y minus is mean, right? Times y minus is mean. Okay. Right? That's how you find the covariance. We see that y minus is mean is y. What is mean again? What is the mean of y again, Panat? The mean of y is, you just calculate it, is x beta, right? So this guy, when you subtract it out, so it's u, the noise term. So covariance of y is actually the expectation of u and u transpose, which is given by sigma. Okay. So you just plug it in, and that is the expression in the bottom. Okay. So let me highlight it here, that the covariance of your beta hat depends on the regressor matrix, depends on the covariance of the noise term. If all the diagonal terms in the noise, like if all the terms are the same, which means all the UI has a uniform variance, which means you can write sigma as a multiple of identity matrix. Can you plug it back here? So what do we have in if a matrix has can be represented as a multiple of I, right? Which means you can put kind of factorial sigma square, and then you have x transpose inverse, x transpose times I, right? Times x transpose x inverse. And the result is trung. Trung.
Yes, Ajahn.
Yes.
Yes.
After multiply this out.
Yes. It's S transpose S. Plus.
No plus. Did you say plus?
Inverse, Ajahn.
Inverse.
Yes.
And then finish or what? Because these term and these term would be cancelled, right? X transpose X time its own inverse with the sigma square. Okay, So we end up with this important result that we have derived the covariance of beta hat, and when the noise term corrupted in the data generating process, if they have uniform variance, the expression of the covariance of beta hat is simplified into this form. So I conclude it in here. Okay, I conclude it in here. And then we have important result that I would like to probably skip this for now. Okay, I would like to focus on it, and this is the result that you're actually going to see it in library software, right? Here's the thing. Okay, if in under this assumption, you have this as a data generating process, the ground truth model, all the UI, okay, all the UI, you assume that it's distributed by normal, okay, and all the UI has the uniform variance, okay. You know that in theory that we just proved, covariance of beta hat is sigma square X transpose X inverse. Okay. Now, if you look at this quantity, y minus x beta y minus x beta hat. Okay, this is called the residual, right? We use I use the notation u hat because it represents an approximate of the error term. Approximate of the error term. If you sum square of the u hat, okay, so this is residual sum square. Residual sum square. Now, if I take the sum square of u hat and I divide it by big N minus small n, it gives me a sense of what? This is the error term, right? Approximate of the error term. But I kind of normalize by how much data I have, like divided by big N. Like just leave the subtraction with the small n for now. So it's kind of it gives me a sense of the average of the what it's like the mean square error. Okay, we can prove in statistic, right? I give the final result here that S square, the S square term, the residual sum square normalized by big N minus small n is an unbiased estimate for the noise covariance. This property means that if I take the expectation of A square, all right, it is equal to sigma square. Okay, not obvious, need to show, all right. We have the second property that so basically what I'm saying is that the S square, the residual sum square divided by big N minus small n here is like an approximate of noise variance after you run the regression. And we also have another result that this quantity, the ratio of A square and with the true noise variance is distributed by chi-square with big N minus small n degree of freedom. Again, this is not obvious, need to be shown. And it requires the Gaussian assumption of the corrupted noise here. In a scientific statistical software, all right, we know that in theory, the covariance of beta hat is given by this term. It looks like we need to know the noise variance in order to determine covariance of beta hat, right? So what I'm saying is that we can approximate the covariance of beta hat by replacing these true noise variance with the S square, which is an estimate of noise variance. Okay, so again, this covariance of beta hat is going to be n by n matrix, right? If we get the diagonal components, remember the covariance of the diagonal of the covariance has to be positive. That's a property of covariant matrix. And of course, we take the diagonal term, we take the square root, and that is the standard deviation, and this is what we call standard error of beta hat. Okay. I'm going to leave this one last note. Okay, that if you look at this expression of the covariance of beta hat, okay, and if you take a look at the matrix, the regression matrix X that has that I mentioned, that you can partition into rows, all right? Because the row represent, you know, that how many samples you have. So if you characterize these X transpose X, you would have X1, X2, Xn, all right? Transpose it, multiply with X. Okay, and if you multiply it together, you're going to have Napat. Napat. Can you multiply these two guys?
Yes, Ajahn. Equal to x1 transpose plus x2 transpose, and so on.
Xn and Xn transpose. All right. My first observation is that the more n you use, the more samples you use. I mean, all of these sum is a sum of positive semi-definite matrix. Think about the X, the vector X is xk is a vector. So this is outer product, right? X is a vector, x1 transpose is like this. So the multiplication is a matrix, outer product. So all of each term, all the terms, these are positive semi-definite matrix. If you make a sum of positive semi-definite matrix, of course the sum is also positive semi-definite. All right. And of course, if you have more terms, like more sufficient terms, you can say that, oh, it can be made positive definite matrix. Okay, but then if you use more term here, like the bigger n you have, like the bigger of the matrix it is. When you take the inverse, right? When you take the inverse, if the matrix X transpose X is big, of course, the inverse is going to be small. Okay, that means that the first interpretation of this expression is that when you use more sample, the covariance of beta hat is smaller. And that is a supporting reason why you should use more samples in estimation. Okay. The second observation is what we already mentioned before. If the predictors are highly correlated, okay, which means the matrix, the regressor matrix X is here. If the predictors are highly correlated, which means like there's going to be some of the two columns, right? Like some pair of columns are almost dependent, which means that's going to make X transpose X ill condition. So X transpose X inverse will be very big. If the matrix is ill condition, its inverse is going to be big. So that means that the covariance is going to be big. You cannot rely on that estimate of the least square. Okay. Probably I stop here. We have more to see, but I think that we can cover it in the next lecture with the topic of the robust regression.